Hi everyone, my name is Sid, and I'll be walking you through part 1 of your Intro to Physics course. First, you'll learn what physics is and why you should learn it. Then, we'll move on to a quick lesson on forces in motion. And finally, we'll end with a quick test. What is physics? Physics is the branch of science concerned with why everything around you moves and interacts with other objects the way they do. For example, why do things fall? Why does a rock sink while a gigantic cruise ship can float? Why do magnets attract and repel? Why can you see a rainbow? Physics is considered to be the second most purest form of study. So what do I mean by that? Well, if you go to different parts of the world, how their country functions, how their people talk, the way they act, they're all going to be different. But math, they're going to be the same wherever you go. For example, a simple math operation like 1 plus 1 is the same here as a different part of the country, or even the world. And that's the reason why if we were to discover alien life form, math would probably be the first way we communicate with them. Second, humans mess things up all the time, and we're prone to error. Physics hopes to learn about the universe without human bias. You'll soon learn that calculating measurements is very important to science and physics. If your measurements are off by a bit, then that could yield significant difference in your results. Next, since this topic is so intuitive, it can strengthen quantitative reasoning and problem-solving skills. This reason may not be as concrete as the other ones, but it is very important. Let's take a different type of science, chemistry. People would tell you what the bonds of the chemicals are doing, but you can never see and intuitively imagine what's going on. In physics, if someone tells you a ball is being dropped at a certain speed or velocity, you can imagine that in your head, and that's why physics is more intuitive. So even if you don't want to be an engineer, physics is still a must-learn for you. Next up, we have famous physicists. You probably all heard of Albert Einstein. You probably all heard of Isaac Newton, or even Stephen Hawking. These physicists were all intrigued by one simple question: how does the universe behave? Why do things work and function the way they do? Speaking of Isaac Newton, let's get into your first lesson on forces in motion. First, let's learn about the types of units you'll see. The first one's a scalar, which has a size or a magnitude. For example, when you say my car is going about 30 miles an hour, you're talking about the speed of your car. The person you're talking to knows how fast you're going, 30 miles an hour, but not in which direction you're going. In other words, they know your magnitude. Compared to that, let's talk about a vector. A vector unit has both the magnitude and a direction. So when you say my car is going about 30 miles per hour to the right, you're talking about the velocity of your car. The person you're talking to knows which direction you're going and the magnitude, 30 miles per hour to the right. You'll see lots more quantities like speed or velocity. Try and identify if it's a scalar or a vector. Similar to speed and velocity, here's distance and displacement. Distance is the total amount an object travels. Compared to displacement, how far and in what direction did the object travel from start to end? The big squirrely line represents the distance, but the displacement is how much you've traveled from point A to your final point B. Notice how the distance is much larger than the displacement. This may not always be the case, but it could definitely happen. Try and identify which of these is a vector and which of these is a scalar. When we're talking about distance, we don't really care in which direction your object traveled, but we do for displacement. Look at this map. This is how Billy gets to school every day. Pause the video and see if you can find out which one is the displacement and which one is the distance. Find out what's the distance he traveled. Welcome back. I'm assuming you gave it a shot. The distance here is the yellow line, which is the total magnitude he traveled. And if you didn't find out yet, distance is a scalar quantity. So he traveled 7 units from his home to a school. When we don't have a specific quantity, like miles or meters, we just call it a unit. Well, what's the displacement? That's the red line, 5 units. But I'm not done. What direction is he going in? Well, to get from his home to a school, Billy displaced 5 units northeast. With that said, you'll know how to use distance and displacement when talking about velocity and speed. I hand you over to Krishna.
Hi everyone, my name is Krishna and I'll be talking about speed, velocity, acceleration. So average speed is considered to be the amount of distance that an object travels over time, so just distance divided by time. And a unit for that is meters per second. So say if I traveled 6 meters in 3 seconds, it would be 6 divided by 3, which is 2, and then meters per second. Velocity is very similar, however the main difference is that instead of distance, you use displacement, and it's the same meters per second. And also another difference is you want to always use direction when you're talking about velocity. So you have to incorporate, say, like 2 meters per second northeast or north. You always have to incorporate the direction. So which one of these, speed or velocity, is a vector and which one of these is a scalar? So obviously velocity is the vector, since as I said before, you do include direction rather than speed, which you don't have to include direction, so it's a scalar quantity. So if it takes half an hour for Billy to travel to school, can you find his average speed? So speed, you obviously use distance indicated by the yellow lines, and since the yellow lines add up to 7, you do 7 meters or whatever, and then a half an hour converts to 1800 seconds, so you do 7 meters over 1800 seconds, and that's all you need to put, to 7 over 1800 meters per second. For its average velocity, you use displacement, so 5 over 1800 meters per second, and you also want to include direction. So since it's going like between north and east, you want to say like 5 over 1800 meters per second northeast. So to take it one step further, we're also going to calculate acceleration, which is basically the change in velocity over the change in time. And this you also want to incorporate direction since it is a vector quantity. So some examples of acceleration are when you drop a ball. So when you drop a ball, the only force acting on it is gravity, and gravity allows it to accelerate. And since when you drop a ball, it gets faster, like the velocity changes each second, showing that there is an acceleration. And similarly with a roller coaster, your velocity is also constantly changing since you're changing direction. Like when you're going on a loop on a roller coaster, that means your velocity changing, meaning that there's a change in acceleration. And similarly, when you're orbiting a planet, like when a satellite's orbiting a planet, the direction's constantly changing, meaning that there is an acceleration. So can you think of any more examples of acceleration? So like to put it all together, a challenge question, you're walking in a circle at 2 meters per second. So what happens to your velocity, what happens to your speed, and are you accelerating? So pause the video now and answer this. So obviously you're changing direction constantly when you're walking in a circle, meaning that your velocity is changing. However, you're constantly going at 2 meters per second. So that means your speed, the magnitude of velocity, is staying the exact same. And are you accelerating? Well, as I said before, the velocity is constantly changing. So yes, there is an acceleration. And now I pass it on to Raghav, who will be talking about more about forces and how that relates to motion.
Hi, my name is Raghav, and I'll be leading you through the third part of this lesson. So now that we've talked about position, velocity, and acceleration, we're going to introduce a new topic known as force. So what is a force? Well, a force is defined as a push or a pull on an object. You can think of forces as imaginary arrows, pulling an object or pushing an object, and in general, just making the object move in some way. You can imagine there's a box sitting on a table, and the box is originally not moving. The velocity of the box is 0. But then you push the box, and you make the box move. Well, you change the box's velocity, and a change in velocity is not an acceleration, if you remember from previously. So, and you also applied a force to the box. So what a force does to the box, it actually changes the box's velocity. If the box is not moving, it starts moving. If the box is already moving, and you apply a force to it, it starts moving even faster. You can also slow down the movement of the box, and that's also a force, pushing it in the opposite direction. You can also change the direction of the object, and that's also a force, because it changes the direction, and a change in direction is also acceleration. So all of these are all ways in which forces change the movement of an object. So if you look at the first image, person 1 is pushing the box from the left to the right, while person 2 is pushing the box from the right to the left. and they're both pushing with the same amount of force. So what do you think is going to happen to the box? Is it going to accelerate or not accelerate? Well, the box is not going to accelerate because the forces are balanced and they cancel each other out. So the box just stays stuck, doesn't move in either direction. But if you look at the bottom image, where the construction workers are both pushing the crate, they're both pushing the crate in the same direction. And so there's kind of an unbalance. There's more forces pushing it left than there are pushing it right. In this case, there's no forces pushing it right. So the unbalanced force, we also call it a net force. And net forces are what causes acceleration. So this box is going to accelerate in the left direction. So now I would recommend pausing the video and see if you can name a couple more forces. Forces are anything that change the velocity of an object, and you can find them everywhere in your lives. So now that you've thought of a few forces on your own, let's come back together and talk about some common types of forces. The first force we're going to talk about is gravity. And so what gravity does, it pulls all objects towards the center of the earth. So like you can see these three kids standing here. They're all being pulled down towards the earth. When you throw an object up in the air, it also comes back down because of the gravity. It changes, it's originally going up, but then it starts going down. And so the direction of the object changes, the speed of the object also changes, there's an acceleration there, and that acceleration is actually caused by the force of gravity. So if gravity pulls all the objects down, why don't these kids just fall through the earth? What's stopping them? What's keeping them on the surface of the earth? Well, what's keeping them on the surface is called the normal force. If you look at this diagram on the right, there's a box, and it's being pulled down by gravity. But at the same time, it's being pulled up by a normal force. And the normal force, the strength of that force, is actually equal to the force of gravity. And so that's what normal force does. It balances out the force of gravity and stops objects from moving through surfaces like tables or even the earth. Another force is friction. What friction does is when an object is pushed in a certain direction, friction pushes it in the other direction, makes it even harder to push it. Imagine you're pushing a really heavy rock and on a bumpy surface. The bumps in the surface cause the friction, and they make it really hard for you to push the box because the friction acts in the opposite direction. And the last force we're going to talk about is air resistance. So if you see this parachute falling, what makes the parachute fall slower than most objects falling to the ground? Well, the force that makes the parachute fall slower is air resistance. And air resistance is pushing the parachute back up towards the sky. There's small particles in the air, and the parachute kind of collects those particles. Those particles get stuck under the parachute, and the particles push the parachute back up. And this force is known as air resistance, and it makes objects that are falling slower. So out of those forces we just covered, we're going to focus on gravity for a second and talk about mass versus weight, which are both closely related to gravity. So if we could measure the amount of gravity acting on some object, like the gravity doesn't act on all objects in the same way. You can try lifting a really heavy object, and it takes a lot more force to lift it up than a light object. And it's because gravity is pulling down the heavy object a lot more than the light object. So we can actually give a name to the amount that the gravity pulls the object down, and that's called weight. So weight is a measure of how much gravity pulls on the object. And gravity pulls on objects in different ways. Objects that have a greater mass get pulled down more. And so what is mass? Mass is a measure of how much substance or how much matter a substance contains. Imagine a heavy box full of a bunch of objects inside of it. It has a very heavy mass, a very big mass, because of all the substance that the box contains. But then think of an empty box. It doesn't have anything inside of it. That empty box has much less matter inside of it, so the mass of that empty box is much lower. So mass is closely related to weight because objects that have more mass also have more weight. But they're not the same thing. Weight actually depends on the strength of gravity. Imagine if you were on the moon. The moon has a much less gravity. Just the force of gravity on the moon is much lower because the moon is smaller. And therefore, if you're on the moon, you have much less weight, even though your mass is the same. If you have a box carrying a bunch of heavy objects on the Earth versus on the moon, they have the same mass because the amount of stuff inside a box is the same. But because on the Earth, there's more gravity pulling it versus on the moon, there's less gravity pulling it, the weight of that box is much heavier on the Earth than on the moon. So here's an illustration showing what we previously talked about mass and weight. So you can see there's a person standing on the Earth and a person standing on the moon. And the mass of the person is about 45 kilograms. Kilograms is the way we measure mass. And on the moon, it's still 45 kilograms because the number of particles in that human doesn't change. The mass of the object, the mass of this human is the same, regardless of what planet they're standing on. But because the Earth has a much stronger force of gravity, you can see the weight, this arrow pulling that person down on the Earth, is 100 pounds. And pound is a measure of a force. So it's about 100-pound force pulling the person down on the Earth. But on the moon, it's only a 17-pound force because there's less gravity overall on the moon. So we know that weight is mostly dependent on two things. It's dependent on the mass of the object, and it's also dependent on the force of gravity on that planet. And we can use a thing called field strength. Field strength tells us the force of gravity on the planet. If you look at the bottom, the exact definition of field strength is how much force of gravity there is for every 1 kilogram of mass. So let's say on the Earth, it's about a 5-pound force for every 1 kilogram of mass. 5-pound weight for every 1 kilogram of mass. And so if there's a person who has 45 kilograms, we can just multiply the 45 kilograms times the 5, because it's 5 pounds per every kilogram, and we get the total weight of that person. Similarly, on the moon, there's going to be less gravity. So we multiply the mass, which is still 45 kilograms, times the field strength on the moon, which is going to be less, and we get a weight, which is much lower. So on the next slide, we're going to talk about a few planets and their field strengths, and we're going to see if you can find the weight of you on each of those planets. So as I've talked about before, the field strength on different planets is very different. On the moon, you can see here, the field strength is about 0.38 pounds per kilogram, which means that for every kilogram of mass, there's going to be a 0.38 pounds of weight. On Jupiter, the field strength is 5.62 pounds per kilogram, which is much heavier. So for every kilogram of mass on Jupiter, there's going to be 5.62 pounds of weight. And on Neptune, the field strength is about 3.1 pounds per kilogram, which means that for every 1 kilogram of mass on Neptune, there's going to be 3.1 pounds of weight. So let's say that you are 45 kilograms. See if you can find your weight on each of these 3 planets. And remember, to find your weight, you can multiply your mass times the field strength of each of these planets. And so pause the video now, feel free to use a calculator, and see if you can find your weight on each of these 3 planets. So once you find your weight on each of these 3 planets, you can see that on Jupiter, the weight is much heavier than on the moon or on Neptune, and it's because Jupiter has a much stronger gravity. But your mass is going to be consistent throughout these 3 planets. Alright, now let's play a game to review what we've learned so far in this lesson. We're going to show you a term, and you'll have to name if it's a scalar or a vector. And for a quick review, scalars are just numbers, like 3 miles or 10 feet, while vectors have both a number and a direction, like 3 miles north or 10 feet south. So the first term is force. Does force have a direction, which means it's a vector, or does it not have a direction, which means it's a scalar? So take a few seconds to think about this one. If you answered vector, then great job, because forces push an object in a specific direction. Think of a box sitting on a table. I can push it away from me, I can push it towards me, I can push it upwards, I can push it in any direction I want. And so forces, they're like arrows, they push an object in a specific direction. And they also have a number associated with them. You can have a strong force, you can have a weak force. So they have both a size and a direction. So they're vectors. Okay, speed is our next one. Is speed a scalar or a vector? If you answer scalar, then great job. Speed does not have any direction associated with it. Like, the speed of an object can be 10 meters per second, but there's no direction. If it did have a direction, it wouldn't be speed anymore, it would be velocity. It would be like 10 meters per second north, and that's a velocity, not a speed. Alright, distance is our next term. Distance a scalar or a vector? If you answer scalar, then great job, because distance is just a measure of how far apart two objects are. There could be 10 meters apart or 10 feet apart, but they don't have any direction associated with that. If it did have a direction, it would be displacement, not distance, because displacement would be like, I moved 10 meters north, while distance is just, I moved 10 meters, so it doesn't have any direction. And the last term is acceleration. This is a tricky one, so think about it. If you answered vector, then awesome job, because if you think about it, forces and acceleration are closely connected. If I have a force pushing an object in a certain direction, it's going to accelerate in that direction. And so forces, since they're vectors, and they cause acceleration, acceleration is also a vector. I can have an object change velocity in a specific direction. I can have it, if it's moving forward, I can have it accelerate even more forward and go even faster. Or if it's moving forward, I can have it accelerate backwards and slow down. So acceleration can be in any direction, and so it's a vector. So that's the end of this physics lesson. We're going to be uploading a few more lessons soon, so stay tuned, and thank you for watching.